Hello, Anatomy and Physiology 1 students. This is your last installment of your muscle lectures. So this one is going to be talking about various concepts in muscle physiology, things like treppe, muscle fatigue, metabolism, and tone, and with a few other things kind of thrown in. So we're going to first start talking about treppe. If I can get your slide to advance. Alright, so first thing I want to talk about is waves, what we call wave summation. That first bullet point up there, wave summation. So this particular word, summation, sum, if you're asked what is the sum of something, then you know you have to add that. So wave summation. What this is when you add more and more stimuli to a muscle, how does that muscle going to react? And how is it going to react as far as force goes? So wave summation, we have another name for that. What we see as a result of wave summation is something that's called treppe. And treppe is a funny little word, and it represents a staircase effect. Okay, so the staircase effect. This phenomenon known as wave summation is when waves of contraction of a muscle add together. So you're basically adding it together. Think of a muscle fiber getting repeated stimulation. So it gets a stimulation, it gets stimulated by a neuron, it results in a muscle contraction, that muscle, and then it gets another one, okay, and then another one, and then another one. And how does that affect the force over time? And what we see is it creates this treppe effect, this staircase effect. So that muscle will have more and more tension over time because of that. So because you're going to have frequent stimulation, because the muscle fiber gets frequent stimulation, you're going to have more and more force over time. So it's a staircase effect. So if you're looking at the graph, right, you see muscle tension and frequency of that stimulation. Okay, that's going to result in a greater tension in that muscle, and therefore a greater force of exertion for that muscle. Okay, so that's wave summation. So in essence, what is wave summation? It is the result of a muscle when it gets repeated stimulation. Repeated stimulation over time. All right, I'm going to make this one small. Oh, hold on. And you guys know I don't, I have to stop this. I don't edit. I know how to pause, but I don't know how to edit. So it's kind of like, you know, real life. It's like a real life lecture, right? I'm going to make this one smaller, make this one bigger. Okay. Next bullet point up there is motor unit. So a motor unit. We have talked about this. And what is a motor unit? Okay, you should already have this in your notes. What a motor unit is. A motor unit is a motor neuron and all of the muscle fibers that it supplies. So this picture right here with the yellow around it is showing you a motor unit. It is one motor neuron and all of the muscle fibers that it supplies. So as those axonal endings start to branch, they're going to branch into that muscle and form a neuromuscular junction with each muscle fiber. Each muscle fiber only needs one neuromuscular junction in order to be stimulated. Okay, so that's a motor unit. Okay, now what is typical? What is typical in a contracting muscle is that we will have multiple motor units acting on a muscle. Okay, multiple, not just one, but we're going to have multiple motor units acting on a muscle. So I really like this graphic down here that shows it well. So here is a motor neuron, and as it goes into the muscle, it branches into the various muscle fibers of that muscle. Here's a different one. Okay, this is a different motor unit, and it's branching through the muscle as well, and it's actually forming neuromuscular junctions with different muscle fibers in the same muscle. So when one of your muscles contracts, it's not just one motor unit, it's going to have multiple motor units. So multiple motor units sending impulses to get those muscle fibers to contract. Okay, and I like that picture because it shows that these motor units are dispersing within the muscle. Okay, when a whole muscle does a contract, you're going to have multiple motor units serving that muscle. And they may not all be sending an impulse all at the same time. You're going to have an increasing number of motor units act in order to make a whole muscle contract. So what I'm saying is that while some units are active, some units might be relaxing, may not be sending an impulse. So for example, this one might be sending an impulse and getting those muscle fibers to contract, while this one is not sending an impulse and those muscle fibers are relaxing. So it's kind of a give and take so that we have multiple motor units. Not all are going to be sending impulses at the same time. They kind of think of them as they take turns doing that. What is the advantage of this? And the advantage is that muscle fatigue is delayed. Okay, so you get a delay in the muscle fatigue. So that's the next thing that I want to talk about, is muscle fatigue. Our last bullet point down here. Oh, all right, I'll do it again. All right, so muscle fatigue. I blew this up so you can see my little cartoon. Side effects include headache, dry mouth, muscle fatigue, and turning into a frog. We do happen to hear that phrase a lot, muscle fatigue, and most often than not, we're kind of using it incorrectly. So we're going to talk about what is true muscle fatigue. All right, what is true muscle fatigue? So this is the definition of muscle fatigue. It is the inability of a muscle to contract forcefully after prolonged activity. So inability of a muscle to contract forcefully after prolonged activity. So we may ask why? Why would that even occur? If what we said was that multiple motor units, some are going to be contracting, some are going to be relaxing in that muscle. We're trying to delay this muscle fatigue. So, two major reasons why true muscle fatigue occurs. Number one is that the muscle has used up most of its available energy and is no longer able to contract. Okay? So we're saying we've used that muscle so much, there is no more available ATP. Okay? We're not making it fast enough in order to provide enough that is needed for those muscles to contract. So the muscle has used up most of its available energy and is no longer able to contract. Right? We need a lot of ATP in order for that to happen. A second reason is that ionic disturbances interfere with calcium release from the sarcoplasmic reticulum. So let's think about that. We know the process. We know that calcium must be readily available in order to bind to the troponin, therefore move the tropomyosin, therefore uncover the binding sites, the active sites on the actin, and allow for that cross-bridge attachment of the myosin heads to the actin, and therefore cause that muscle shortening, that contraction. So if we don't have that calcium, if something's going on and that calcium can't be released, then you're not going to have that either, right? So those are the two reasons why true muscle fatigue can occur. All right, so let's move on to muscle metabolism. So in muscle metabolism, we're asking the question, where do we get the energy to run our muscles? Where specifically are we harvesting the ATP, making the ATP, in order to get our muscles to contract? Okay? And three possible ways, okay? Oh, I just realized something's wrong on this slide. So let me pause this. I'll try to fix it. We don't need 2 3s. Okay, now we have 3. So number one we call the phosphagen system. Now for this is also known as substrate level phosphorylation. So substrate level phosphorylation. And we're using what's called the phosphagen system. So inside of our muscle fibers, we make this molecule called creatine phosphate. Okay? So we make this molecule called creatine phosphate and we store it locally there inside the muscle fibers. This creatine phosphate does something for us. Now we don't make tons of it, but we make some. And once we've used up some ATP, you know that once we use ATP, we use up the ATP and what we're left with is adenosine diphosphate and some phosphate. We've broken off that phosphate and used that high energy from breaking the bond. Alright, so this creatine phosphate that we make and store inside the muscle fiber, what happens, oh, and I just noticed that I messed up our little equation here, and we're going to go in and fix it. And you're coming with me. Alright, so we take creatine phosphate, and what it does for us is that we add in some ADP, adenosine diphosphate. It's going to be readily available there in the muscle fiber because we've just used a molecule of ATP. We're going to mix those two together, undergo a chemical reaction. Okay, these two. We're taking these two, undergo a chemical reaction, and what we get is some very quickly made ATP plus some leftover creatinine. Okay? So inside of our muscle fibers, we're going to take some creatine phosphate, add it to ADP, undergo a chemical reaction, and we're going to get some ATP and some leftover creatinine. What's the most important thing here? We're getting some readily made, very quickly made ATP. This ATP can now be used for that muscle contraction. As a leftover of that chemical reaction, we make creatinine. Creatinine goes out of the muscle fiber and into the bloodstream, okay? And we get rid of it. We get rid of creatinine. We don't like creatinine to build up inside the blood, okay? So we actually filter that out. So in essence, what has this creatine phosphate done? It has donated its phosphate to ADP, and so that we can make some very quick ATP. All right, we got some little waste product here, and we'll get rid of that waste product. All right, so right inside the cells, very quick way to make some very fast ATP. Now, how much of this creatine phosphate do we store in the muscle fibers? Not too much, but enough for about 10 to 15 seconds of muscle contracting, okay? So we're getting some very quick ATP regeneration. We're getting some, 10 to 15 seconds of being able to use our muscles. All right, another place where we're getting energy to run our muscles is what we call the glycogen lactic acid pathway. Now you already know this. We've been through all of metabolism, cellular respiration before, and this includes glycolysis. One of the major things I know that you remember from glycolysis is that it's anaerobic. What does anaerobic mean? It means that it doesn't require oxygen. So glycolysis does not require oxygen. It can run in the presence of oxygen, of course, but it doesn't require oxygen. Okay? So it's breaking down glucose, and in essence, we're getting those high energy electrons. We're getting a tiny bit of ATP, but we're still getting something. It provides us with about 30 to 40 seconds of energy. Okay? And just remember, all the time, glycolysis is running in the background. It's always running, no matter how much of the oxygen is coming in. We're getting glycolysis. Glycolysis is running. Okay, the third one. Aerobic respiration, number 3, is where we're going to gain the most ATP. So in aerobic respiration, what are you thinking about? You're thinking about the citric acid cycle, also known as the Krebs cycle. We're thinking of the electron transport chain. Where does the electron transport chain occur? Do you remember? It occurs at the cristae of the mitochondrion. So thankful to our mitochondrion that we can produce the vast majority of all of our ATP. And we're using those high energy electrons in order to make that ATP. So in most activities that are going to last more than 5 to 10 minutes, aerobic is going to kick in. And it provides us with the most amount of ATP. Being aerobic respiration, what else does it rely on? What else must we have in order to make all of that ATP? Oxygen. I think you probably got that right. We need oxygen. So oxygen is our terminal electron acceptor in the electron transport chain. As long as we are providing oxygen all the way to the inside of those mitochondria, inside the mitochondria, okay, we can continue to make ATP. Okay, two sources of oxygen to muscle fibers. So, these are the molecules that are going to bind to the oxygen. There are two. So we have hemoglobin and myoglobin. So first, hemoglobin. Hemoglobin is a molecule that is found in red blood cells. Red blood cells are chock full of hemoglobin, and hemoglobin will bind to oxygen. Okay, binds to oxygen, delivers it to various places in our body. It's one of the ways in which oxygen travels in our blood. So a second one is myoglobin. Myoglobin is a molecule that's found in the muscle fibers. I introduced you to myoglobin in a previous lecture. And myoglobin is only found in muscle fibers. It is a pigment. Both of them are pigments. And it will bind oxygen there inside the muscle fiber. Remember I said it's kind of like a storage closet for oxygen, because when muscles contract, they need a lot of ATP. So we have a lot of mitochondria in the muscle fibers. And lucky for us, we have this myoglobin there inside the muscle fiber that will hold some extra oxygen for us. Okay, so we're increasing that oxygen readily available there inside the muscle fiber. Kind of cool. All right. On to another concept that we call recovery period. And an older term for this, an older phrase, is oxygen debt. So way back when, we used to say we're paying our oxygen debt. Now, what I want you to imagine is that we're exercising on the treadmill. And we get done exercising, say we've been on that treadmill for a while, and getting really tired, and jump off the treadmill and we sit down, but we're still breathing like we are on the treadmill. Okay? Way back when, in the rec center. I know you guys, this is before your time, but like if you walk into the rec center, you know, like if you keep walking like towards the basketball and the televisions are there on the left, well, I know now they have the treadmills and the steppers there, but there used to be couches there. Okay, couches. And so I would get on the treadmill, I would get on the treadmill and then it'd be on the treadmill for a while. Well, immediately when I get off, of course I would go sit on the couch. But think of maybe the last time you were exercising, you stopped exercising, you sit down, and your heart rate is still up, it's elevated. You're still breathing, kind of like you're exercising, but you're just sitting and clearly not contracting those muscles. So you have an increased ventilation, you have an increased heart rate, and you're kind of huffing and puffing. For me, it takes quite a while. I do that for a while. For you, probably not. Now, we used to say that you're paying your oxygen debt. So that's going to happen until you've paid your oxygen debt. We don't necessarily call it that anymore. We call it the recovery period. Now, there's 3 things that's going on during that period of time where you're not exercising. You may even be laying down, but you're still breathing and your heart is pumping like you are. Okay, that particular experience. So there's 3 things that are going on during that recovery period. Number 1, you're converting any lactic acid that was created into glycogen and is storing it in the liver. Like I said, most of the lactic acid that is produced in those muscle fibers, when it has temporarily run out of oxygen and undergone fermentation, is stored in the liver. So it's going to the liver, it's undergoing a conversion and being stored there. Number 2, we are resynthesizing our creatine phosphate stores in the muscle fibers. So remember, that was one part of our muscle metabolism where we gained about 10 to 15 seconds of ATP. We only have a little bit in those muscle fibers, but that's one of the things that's going on. We are resynthesizing the creatine phosphate and kind of repacking those stores of creatine phosphate. Number 3, we are replacing the oxygen stores bound to myoglobin. So kind of resetting, redelivering that oxygen to the cells, to the muscle fibers, and reloading that myoglobin into the muscle fibers for the next time that we're going to exercise. Now, I said that, gosh, for me, it takes a long time. So I kind of breathe. I'm still have that increased ventilation. My heart rate's still up. I'm still huffing and puffing for quite a few minutes after I exercise. And I said, probably not so much for you. Well, here's the thing. You're probably more in shape than I am. I can pretty much guarantee that, right? So, the more you exercise, here's the thing. The more you exercise, the more efficient your body gets at this recovery period. Okay? So let's look. The more you exercise, the more, of course, we always hear that exercise is good for us. And what does exercising do for us? The more we exercise, the more efficient that our body gets at circulation, so delivering oxygen to the inside of those cells. Okay? The more efficient that our body gets at delivering oxygen to the inside of the cells, the less fermentation is going to occur. Therefore, the less lactic acid production will occur. Okay? So maybe the more you exercise, the less lactic acid you're going to create that has to be turned back into glycogen, or turned into glycogen. Okay? So the more you exercise, the more efficient your body gets at delivering that oxygen to the inside of the cells. Okay? And the more that you exercise, you will decrease the amount or the time period for that recovery period. And you probably noticed that. So maybe you haven't exercised for a while, but now you're going to get back in the groove of it. And the first week or so of you exercising, man, the recovery period's lasting a long time. But if you keep doing it, guess what? You may or may not even have a recovery period. Or you don't notice it as much, I should say. So your body gets really good and efficient at that. I put this cartoon down here because that's what I feel like after exercising. Alright, next thing we're going to talk about is muscle tone. So what is muscle tone? And we can all imagine when we think of muscle tone, we kind of think of someone who is toned, right? What is muscle tone? And if I had to describe what it is, it's a small amount of tension in the muscles. They're slightly contracted muscles. So you might think of someone who is kind of like just standing there and not working out. And you can see a definition of their muscles. Okay? So see a definition of their muscles when they're not intentionally contracting them. Now, I like to, when we talk about muscle tone, a lot of times you think of people, they might have, okay, well, do I have muscle tone or don't I have muscle tone? And if you do have muscle tone, kind of like the pictures what we're imagining, we can see an outline of the muscles underneath the skin. Okay? Now, as it turns out, everybody has muscle tone. Everybody does. It's just the degree of how much muscle tone do you have. Now, of course, some people don't have muscle tone, and they have disorders which may cause that to happen. But for everyone else, you do have some degree of muscle tone if your muscles are still working properly. However, like me, you don't really see my muscles under my skin slightly contracted. Mine have a layer of probably fat, right? We have the skin, I have a layer of fat, unfortunately, and then I have my muscles. So even if my muscles were slightly contracted, still not going to be able to see that. Now, the more you use your muscles, the more muscle tone that you're going to have. Now, muscle tone, it's going to occur. We're going to see these slight contractions in the muscle when we're not intentionally contracting our muscles, not voluntarily contracting our muscles, okay? This is due to a spinal reflex. I know you know what spinal reflexes are. You talked about those in lab. And the more that you use that muscle, the more of that spinal reflex will occur. Think of that spinal reflex being there as it's priming the muscle and being ready to contract, okay? But the more that you use that muscle, the more muscle tone that you will have, okay? So the more contracting that it will do from the spinal reflex. I hope that makes sense. The muscle, in turn, is ready to respond to stimuli. All right. Now I have types of contraction here, and I don't think that we're going to have types of contraction on your exam. So I'm going to delete this. We don't need that. I'm going to add in a new slide. And before I let you go, we are going to talk a little bit about the turkey, right? Because Thanksgiving is coming up. And I know you guys I hope that you guys have a very good Thanksgiving. And I hope everybody stays healthy. Now, white meat, dark meat, okay, in the turkey. And our turkey, so who likes white meat? Raise your hand. Okay, who likes dark meat? Raise your hand. Isn't this fun? Who likes both? Doesn't care. Alright. So, here's the thing. Now, if we look at the turkey, and there's different parts of the turkey. So the legs are going to be dark meat. The thighs, they're going to be dark meat. The breast for sure is white meat. Okay. Now, if you've ever these will actually these will take on a different taste. All right. Sometimes it's described as the dark meat takes on a more meaty taste because it's hard for us to describe that taste. And some, people who like dark meat, when they taste white meat, they're like, yeah, this is bland. This doesn't really taste like anything. So everybody's going to have a different take on that. Everybody's going to have a different like, depending on their tastes. And so, talk about that at Thanksgiving. And why am I even bringing this up is because now you can understand why we have white meat and dark meat. Or if we think about this, I'll just tell you this. the reasoning why the dark meat is so much darker is because it has more myoglobin. That molecule that we talked about that's located inside the muscle fibers that attaches the oxygen. It's kind of like the storage closet for the oxygen. Makes it an extra oxygen on the inside of those muscle fibers. It's a pigment, okay? It's a pigment that's going to attach that oxygen. And so when you have lots of that myoglobin, okay, it's going to show up in the appearance of the meat. So dark meat has much more myoglobin than white meat that has very little, if any, myoglobin. All right? Now let's look at that turkey. A turkey does a lot of walking around, okay? And this is where we're mainly going to find a lot of this dark meat. So the muscles that need to be used quite often, okay, are going to be the dark meat on that particular bird, right? Turkeys, do they do a whole lot of flying around? We know they walk a lot, but do they do a whole lot of flying around? No, right? You see them gliding sometimes, but no, that's not their main form of getting around, right, throughout their life. So their breast meat doesn't have a whole lot of myoglobin as a result of that. So when needed for sudden outbursts of muscle-needed contractions, it's going to rely on some of these extensors that they have. They're going to rely on the legs, of course, ready and primed, have that oxygen there. It's going to need a lot of ATP, and we're going to see dark meat. Doesn't often use the breast. Okay, so it doesn't have that myoglobin in it. So now you know. Lots of myoglobin, not so much myoglobin. Okay, now you get to impress all of your family at Thanksgiving, right? So if your parents or maybe you are cooking up a turkey, right? Cooking up the turkey, thawing out the turkey, what usually happens is that they're going to take the neck and maybe not, take the organs and put them in a bag, and then they take that and put it inside the turkey. So once your turkey thaws, you're going to pull all of that out of the turkey. Some people like to cook with the organs. Some people do, some people don't. So they will go ahead and include those organs in the turkey and the neck. If by chance your family doesn't cook with the organs, get those organs out of the bag, right? Get those organs out of the bag, and I want you to look at them. So you'll find the heart, you'll find the liver. Those are kind of neat to see, right? You can see it, you can touch them, you can feel them, you can point out the parts to your family, right? They're going to be so impressed that you can do that, right? But kind of like dissecting our little turkey before we cook it. All right. So that's it for today. That concludes our talk on our lectures on muscle. The next lectures that I'll be starting on soon are we're going to be starting the cardiovascular system, right? We're going to talk about the heart first. So everybody have a good Thanksgiving, and I will get up the next set of lectures as soon as I can. Thank you, stay safe, and please stay healthy.